Hello, let's go ahead and talk about the inputs that you will most likely have when you deal with AC circuits. So obviously the inputs are going to be waves, sine or cosine, and you know by now that a cosine wave is a sine wave with a phase shift. So we're going to talk about those inputs in terms of waves for the voltage, for the current, and this will give us a pretty good introduction about circuits, where the first thing that we're going to learn how to deal with is the input. So the goal is to become familiar with the characteristics of waves and the waveforms, including the general form and how to get the average value, since very likely you have heard the RMS value of the voltage or the current, and RMS stands for the root mean square, so that when you buy a product, an appliance, an equipment, they give you a voltage rating. But since most likely it's going to operate on a AC voltage supply, the RMS is a single value that is the average of the voltage that the equipment sees for the operation. Another goal is to be able to determine the phase relationships, the phase shifts, and the frequencies that the wave carries. So depending on the circuit or the system, there are different types of frequency domains or frequencies that you deal with. So for voltage into your appliance, into your system, most likely the frequency is fixed to 60 Hertz. But if you're dealing with an amplifier, then the voice has different frequencies, and in that case you modulate the frequency, and we'll learn about some tools to be able to clean or get the average or manipulate the input if the frequency is not fixed. Also, we want to learn how to calculate the effective values of the wave, and as I said, the RMS or the average. And we want to become familiar with the instruments where you are able to use that you use to be able to measure the voltage and the current, the resistance of the system, for a resistor, a capacitor, a diode. And most likely that's going to be through multimeters, and wave generators are going to help us determine the voltage coming in. But using the multimeter and spectroscopy or oscilloscope, we should be able to determine the outputs as well. So let's start by the very beginning. A wave, I'm sure you've seen this many times, and this is going to be a review in terms you don't use waves very often. As you know, AC circuits have an input of voltage and current in terms of a wave, and that wave can be described as a sine wave because it has all the properties of a trigonometric function characterized by a sine function. So the first thing that we want to know is that we want to recognize the cycles, and cycles is a term that you use for revolutions, which is closely related to radians, which is closely related to waves. And we want to know what is the period, what is the frequency, so all those things are related. So cycle is nothing more than the distance between two similar points. So notice that this point right here is where the wave starts, and this point here is where the wave starts again. So this has a little offset. This one right here is a cosine wave, I can tell, because it's one exactly at this 0 point. So this is the starting point, and this is the starting point. This is a cycle. So the period is the distance between the beginning and the end of the cycle. Okay, so that's applicable for any type of wave. So this is a sine wave, where this right here is the period from the beginning to the end, and the period is shown by T3. T, capital T, is the period, and we have to be careful. Capital T could also be temperature, but we don't call period with P because P is also pressure. So just be very careful that when you see T in electromechanical systems, T is period, but depending on the problem could also be temperature. So be careful there. Lowercase f is always frequency. That is reserved for values of frequency, and the units are hertz. So 1 hertz, or 1 hertz, sorry, hertz, because this comes from my last name. Last name is Hertz. 1 hertz is a cycle per second. So if this distance or this cycle happens in 1 second, this has a frequency of 1 hertz, this wave. But if there are 2 cycles in 1 second, then the frequency is 2 hertz. Okay, so for instance, this is 1 second. Notice that is the distance. There's 1 second between this beginning point and this end point that we're recording for your experiment or for your project or whatever it is. This is the interest. The value of interest is 1 second. And notice that the period is half a second, meaning that the wave, there are 2 waves, there are 2 revolutions, or there are 2 developments of the same wave in 1 second. So in other words, this happens 2 times in 1 second. In 1 second. Okay. This one here is a little bit tricky because this one in 1 second, the period happens in 0.4 seconds. All right. So the way to determine the cycle, the frequency, is based on the cycles or the period. So this is pretty simple. In 1 cycle we have 1 period, and all these T1, T2, T3, it's pretty simple. It becomes a little more complicated when they're not evenly distributed, such as this case where in 1 second we have a period that it took 0.4 seconds. Okay? So for example, what is the peak value of this sine wave that we capture for 1.4 seconds? Okay, so this wave could go on forever, kind of like a wave of light, but we're only interested in 1.4 seconds. So the time domain is from 0 to 1.4 seconds, and the amplitude, what is the peak value, is 8. So 8 and -8 are the values of interest in terms of the peak values. What is the instantaneous value at 0.3 seconds and 0.6 seconds? So at 0.3 is right here. So if you notice, the wave has a value of -8 volts at 0.3, and at 0.6 has a value of 0 volts. What is the peak-to-peak value of the waveform? So this is peak-to-peak, sometimes called VPP, capital V, lowercase pp. And so the voltage peak-to-peak is 8 plus, or initial minus final. So 8 minus 8, that is 8 plus 8, 16, so 16 volts. What is the period of the waveform? So the period is, let's see, we have 1, 2, 3.5, so 3.5 cycles. Yes, 3.5 cycles. And what is the frequency of the waveform? So the frequency is, so we know the frequency has units of 1 over seconds, that's hertz. So we have to do cycles divided by time. So cycles is 3.5 cycles and time is 1.4 seconds. So let's go ahead and compute that. And the way we do that is period equals 3, or cycles, 3.5. And remember, this is Google Colab. You just need to get an account with Gmail, and you should be able to use this for free. This is a pretty good way to perform calculations if you don't have a calculator. If you have a calculator, you don't have to worry about this. But since I want to share my screen and I don't have a scientific calculator emulator, then I'm gonna use Python and Google Colab interpreter to show you. And then time equals 1.4. Okay, so units here are, I'm gonna put a comment, no units, and comment units of seconds. So frequency equals cycles divided by time. And then comment is not going to be interpreted by the API, so this is just something there for us to know what's going on in the code in case we come back later and we want to know what's going on. So units are 1/seconds, which is just the same as hertz. Print my value of frequency, and we should be able to run this. F has value of 2.5. Okay, what does this say? 2.5. Excellent. So 2.5 is the answer to what is the frequency of the waveform. Alright, so talking about waves, where do we use waves and at what frequencies? So remember that the wave that we characterize mathematically has three main parts. One is the amplitude, which in this case we were talking about an example in terms of voltage, but it could also be current and could also be power or watts. So voltage is one characteristic. The other thing is the frequency. So in the example we just saw, had a frequency of 2.5 hertz. And in the other case is the phase. So, and that's a little more detailed about the waves, and that usually corresponds to a system where a wave coming in as the input is transformed either by a capacitor, by inductor, by something, and they shift, so there's a phase difference. But mostly talking about frequency, we use waves for different applications. So for instance, between 1 hertz and 10 hertz, remember the example we just had was 2.5 hertz. So between 1 hertz and 10 hertz, between 1 hertz and 100 hertz, we see the voice that we our human voice and dogs barking and things like that. Between 15 hertz and 20 kilohertz, so 20,000 hertz, is most of the things that we can hear. So anything that is quieter, everything that is more than 20 hertz we won't be able to hear, even though some other dogs, for instance, they can hear other higher pitch frequencies. We won't hear more. On average, we hear between 15 hertz and 20 kilohertz frequency waves. Now the amplitude, units of sound, for instance, is decibels, dB. More than 120 decibels is pretty dangerous for our ears. So regularly our ears are sensors that can take waves between 50 hertz and 20 kilohertz at a range of between 40 decibels to 120 decibels. Alright? Between 100 kilohertz and 1 megahertz, between 0.5 megahertz and 1.7 megahertz is what we call the amplitude modulated. This is AM radio, and amplitude modulated waves is, let me go ahead and use one note. And I'm gonna try to use the stylus here. Let's see if it works. Yes, it does work. Okay. Excellent. So let's say we have time and let's say power, which we'll talk about power later. Before, when we talk about DC circuits, we know that power is equal to V times voltage times current, right? But now these are waves, okay? Before they were just numbers. So let's say in AM radio, amplitude modulated, you have waves that are different, the same frequency but different amplitudes. Okay, so these are supposed to have the same frequency, meaning that the cycles in 1 second are always the same, but the amplitude varies. Okay, so this is the range of amplitudes, and you know, we have some very high amplitudes, very low amplitudes, and this will be the voice tone, and if somebody's screaming versus somebody's just whispering. Okay, so this is AM radio, which, if you notice, if you go back to the radio and you dial AM radio is noisy, because noise, it's a rule of thumb, noise develops on amplitude, not on frequency. So if you have your amplitude wave over here, the more you drive further away from the station, the noisier these waves can become. So if you're by the station, this looks like that, but if you are far away from the station, then it will look like this. The same signal, it will look like this. So high up here, high up here, high, high, distortion. Okay, so it will be supposed to be the same wave but with more amplitude. The issue here is that this is going to be very noisy, okay? Because, as I said, and we'll talk about this later, noise carries on amplitude, not on frequency. That's why when you go to FM radio, and we'll draw FM radio over here, FM radio, this is time and this is power, you have the same amplitude, but the frequency is different. Okay, the same amplitude but the frequency is different, so the signal is modulated with the frequency. Okay, and this is great because voltage only carries, or power or noise is carried on with amplitude. The frequency has no substantial noise. And if we go back to the presentation, we see that FM radio is between 88 megahertz and 100 megahertz. So between 0.5 and around 2 we have AM radio. Between 88 and 100 megahertz we have FM radio. Alright, so also between 300 megahertz and between 300 megahertz and 300 gigahertz. So this is 300 e to the 6, megahertz is e to the 6, and gigahertz is e to the 9. This is what it's called the microwave range. Even though our microwaves, in the kitchen, only operate around 2 gigahertz, this is all the microwave range, and this is used for experimental measurements. This is used for a lot of other applications that are not just cooking stuff. Then we have different types of waves that are by the standard in the electronics, or IEEE, the Institute of Electronics Engineering. You have ELF, which is extremely low frequency, which is what humans can hear. VLF, which is very low frequency, which is about the beginning range in radio waves. We have low frequency waves, which is between 30 kilohertz and 300 kilohertz. We have medium frequency, which is 300 kilohertz and 3 megahertz. We have high frequency, which is 3 megahertz and 30 megahertz. Notice that at this point, this was back in the 60s, even probably 50s. So at this point, these were very high frequencies generated by the hardware. At some point, we're going to start talking about later this semester how to generate these waves. Because yes, mathematically you can describe them, and yes, we know they exist, but how can you generate the waves? Well, you shouldn't be surprised to hear that you generate those waves with circuits that have capacitors and inductors and rotating parts to generate a signal. So the receiver, which is another circuit, will capture those waves that are generated by a circuit somewhere else in the world, well, somewhere else nearby a tower or something, right? So that to say that back when, in the 50s and 40, in the 40s was when FM was discovered. And surprisingly was not very used because people were reluctant to use it, even though now we know that it's much better than AM. Before, radios only had AM radio. FM was a new development in the 50s. Then at that point, the most advanced frequency they could get was what it's called the high frequency, 30 megahertz. And of course, when FM started to be used, or when people started to use FM more often, not surprisingly, the military was the first one to start, to be able to research and expand the use of FM waves. Then it expanded all the way to 100 megahertz, and that's what it was called, the ultra high. And then at that point, based on the hardware, only frequencies up to megahertz were able to be able to generate. The hardware was only able to generate the frequencies in the megahertz range. But later, when FM radio and military started to do research in FM radio and FM waves, then they were able to create more hardware to generate waves with higher frequencies. And that's where we went from very high frequencies to ultra high frequencies, which is 300 megahertz to 3 gigahertz. And that's where microwave for cooking that was developed. Microwave for cooking operates at a fixed frequency of 2.42, 2.45 gigahertz. That really depends on the manufacturer. And then we were further able to develop super high frequency waves that go from 3 gigahertz to 30 gigahertz that are used for a lot of the experimental things that we do with spectroscopy. And of course we have the extremely high frequency, which is from 30 gigahertz to 300 gigahertz. Okay, so you can go ahead and you can research what are the LTE and the 5G, what are those waves in terms of frequencies, because those are, if you think about, they're like airplanes flying, that they don't intersect each other. So some waves are reserved, or some frequencies and bandwidth are reserved for telecommunications, for radio, for cell phone, etc. So for instance, TV works between 54 megahertz and 88 megahertz, and they're modulated so that if you go up one channel, the frequency goes up as well. And that basically says right here, channels 14 to 83 go all the way to 890 megahertz, so almost 1 gigahertz. GPS works at 1.5 gigahertz. Okay, so satellites are transported back up to low Earth orbit, where they have to do their capturing data, or they're receiving the data and then sending it back to the receiver here on Earth. They operate at 1.5, 7, 1.6 gigahertz. The 1.45 is microwave oven, we just saw that. Wi-Fi is between 2.4 and 5.9 gigahertz. And the cell phone is between the voice signal is between 800 megahertz and 1900 megahertz. So this is some of the spectrum for the waves that we have currently in our spectrum, in our air flowing through the air that we breathe. They are constantly going back and forth. If you think about it, in your house you have Wi-Fi waves, you have Bluetooth waves, we have phone waves, and some of them are through the air, some of them are through hardware and wires, like the TV. If you still, well, now TV is optical, but back, old TVs, they were waves through the wire that you had to connect to through. If you think about a TV, the old TVs, they had antennas, and those antennas were transmitted the waves through the air basically, and then you move your knob and you can tune to the channel based on the waves, and that's why you had to move the antennas back and forth. So those are, I don't know if you remember those, but they did exist. The pretty old TVs. Alright, so find the period. This is an example. Find the period of the waveform with a frequency of 50 Hertz and another one with 1000 Hertz. So A, 60 Hertz. 60 Hertz is the frequency of the voltage for the power that we get in our house, in our college, basically for in America and South America and some parts of Europe. I'm not sure if some parts of Europe, but I'm sure Canada, US, and South America and Mexico, Central America, those are 60 Hertz waves, electricity of the voltage, the power. By standard, those are generated at the power plant at 60 Hertz. In Europe and Asia, they are at 50 Hertz. That's the standard they decided to follow. That's why, for those of you who have been to Europe and you take your regular iPhone charger or your computer charger, they don't work. You have to buy an adapter at the airport or before you even go to plug in your product or your cord, because the sockets are different, because the frequencies are different. So even though the voltages are relatively similar, the frequencies are different. So by standard in the US, the voltage that we get at the transformer for a house and most industrial applications work at 60 Hertz. Okay, so the question is, we'll find the period if the frequency is 60 Hertz. The solution is obviously the period is 1 over the frequency, so it's pretty simple. 1 over 60 is 0.016 or 16 milliseconds. And for B, 1 over 1000 is 10 to the negative 3 seconds, so 1 millisecond. So 1000 Hertz wave has a period of 1 millisecond. Okay. Another example. Determine the frequency of the wave. And this is a pretty simple example. If you notice, we're gonna start from 0. So all of this before 0 is just to confuse us. And from 0 to 35. Even though we know that we could compute all the way up to here, and in fact we should be able to go up to here, because if you notice, the first cycle goes here and the second cycle ends here. So this is a difference of 10, therefore this is, so goes all the way from 0 to 40. Okay, so determine the frequency. First of all, we're gonna figure to know the frequency, we need to know the cycles. So we're gonna do 25 milliseconds. The units of time here are milliseconds. So the first thing that we can do is find out what is this point right here. So is 25 minus 5, or 35 minus 15, which is 20 milliseconds, right? Another way to see is visually just determine that this point right here is 15, this point right here is 25, and they're symmetrical, So the middle point between 25 and 25, between 15 and 25 is 20. And then we can say, okay, between this peak and this peak is my cycle, and that's going to be 20 milliseconds. Is what we get. So the period is 20 milliseconds. Okay, so we just need to do the only thing we need to do is 1 over the period is 50 hertz. Okay, as we said, 50 hertz is the common waveform that they use in Europe. Another way that you could have done this is is the same thing. This is the simplest. You're simplifying and saying, okay, one cycle took 20 milliseconds. But another way you can do this is, okay, what's the total amount of seconds that in the total amount of cycles? So we're going to start from 0, and we're going to go all the way to the same point at, this is going to be 40 milliseconds. Remember, because if this is 20 and it's the same frequency, it's not modulated frequency, and this is 40 milliseconds, then we have one cycle, 2 cycles. So it's going to be 2 cycles divided by 40 milliseconds is the same as 1 divided by 20, or 50 hertz. Okay. Alright, so as we said, we use those voltage and current waves as inputs, because that's the way waves are, or the power is sent to our house. They're sent to transmission lines, they get to the transformer, the step down in voltage, which, by the way, we'll talk about transformers later this semester, later maybe even next week, depending on how much progress we can make this week. And those waves carry the same frequency, 60 hertz, all the way from the power line at 450 or whatever voltage they carry. They step down to the transformer back to 120 or 240 volts, depending on the application. So we get, say in my house, I get 120 volts from the socket. Well, those 120 volts AC are used for my washer, for my dryer, for my dishwasher, and that basically is the input to a lot of my circuits. Okay, so the input for the circuit, but the circuit has resistors and inductors and capacitors, and that's another thing that we will learn, is what happens when that wave is the input to the circuit and has capacitors and inductors in series, or capacitors and resistors in parallel. So those are the details that we're going to be learning, but for now let's focus on the characterization of the input. And for that we have to talk about radians. Radians is a unit of distance in a circle, or an angular distance, and we know that 1 radian is 27.3 degrees, hence 2 pi radians equals 360 degrees. Okay, so the way you transform radians to degrees and degrees to radians is this. Radians is equal to pi over 180. That's always the case, because you have to transform degrees to radians by using the 2 divided by 360. So radians equals pi divided by 100 degrees times the degrees that you have. So degrees and degrees cancel, and then you have radians in units of radians, right? And degrees is going to be the opposite. Is 180 degrees divided by pi times the radians. So if you have 17 radians, then you want to transform to degrees, you do 17 times 100 divided by pi. And the opposite, if you have degrees and you want to transform, you're going to get the radians, say 30 degrees times pi divided by 180. That'll give you the answer in radians. Okay? And that is because you can use 2 domains to characterize waves: degrees and radians. So taking a sine wave, which is example A and B, a sine wave starts from 0, and at 0 it has a value of 0 volts or 0 current. Remember, the y-axis, the vertical axis, could be voltage, could be current, could be power, could be sound, dV, could be different things. decibels, right? So this is a sine wave where, for example, voltage is 0 where at a starting point. In terms of degrees, you can have all the way to 360 degrees, which is a full wave. If you notice, if you move this point back to this is give you the area of a circle. Okay, so 180 is the middle point, and in radians you can do the same thing where 180 is pi and 360 is 2 pi. Okay, pi number is 3.14, 15, 16, etc. So you have both ways of characterizing a wave. So be careful when they give you the input to the sine wave. What are the units? If it's radians, if it's radians or degrees, because sine of 30 degrees is not the same as sine of 30 radians. They're different. So that's main confusion most people have issues with. So be careful with those details. And those things are useful, the degrees and radians, because you can compute the velocity or angular velocity of equipment or things like the earth rotating, motor rotating. This has angular velocity, and the distance is in radians per second and revolutions per minute and degrees per second, etc. So angular velocity is the distance traveled within the circle divided by time. The units are, as I said, degrees per second or radians per second or revolutions. A revolution is a whole cycle, revolutions per minute, etc. And of course you can have a quarter of a revolution, a quarter of degree, etc. The angular velocity is expressed as omega. Omega, it's often called angular velocity, and alpha is the distance in radians. Time is lowercase t. So if you want to know the distance traveled within a circle, you simply have to do omega times t, right? So omega, you've seen this many times, can also be expressed as 2 pi times frequency. This has units of radians per second. And these 2 times pi times frequency should be pretty familiar because this is an input to the sine wave, which we'll see in a few minutes. So evidently this could also be expressed as in terms of period. Period and frequency are connected. So omega can also be 2 pi divided by frequency divided by period. So sometimes you have the period but you don't know the frequency. You can compute the frequency, or you can get the angular velocity directly from the period. So for example, we have a full revolution, 360 degrees, and one period will be the full 360 degrees revolution. So the time that it takes to do that is your angular velocity. So if it takes you 1 second to go full circle, then you have 360 degrees in 1 second. That is your 360 divided by 1, 360 degrees per second. And you can transfer the degrees back to you can transform the degrees back to radians, and that will be your radians per second. You can get your revolutions per minute, etc. So we've talked about AC because of the alternating current and the alternating voltage. The reason it's called alternating is because it goes positive and negative, right? The amplitude is symmetric, so ideally you're gonna have positive, say 120 volts, negative 120 volts. The frequency has to be expressed as well. So for the power, the voltage in your house, the frequency is fixed, as we said, at 60 hertz. So if I ask you in a quiz and a question for the exam, what is the standard voltage, what the standard frequency U.S. Industry, U.S. Homes and apartments, it's going to be 60 hertz. Now the voltage is usually 120 volts, And that really depends on the transformers and things. Could be all the way from 115 to 130 volts. So by rule of thumb, the RMS is usually 120, and we'll talk about that also. So you express this wave right here. Remember, this is could be radians or degrees. So depending on what domain you're using, radians or degrees. And the way to express this wave is the amplitude, AM, which even though has positive and negative values, you just express the amplitude as a positive number, times the sine, because this is a sine wave. If it starts from 0, it will be sine. If it starts from 1, it will be cosine. If it's some other value, then it's shifted. And you can transfer sine waves to cosine waves. We'll see how. So if they give you a cosine wave, you can pretty much just take it back to a sine wave, because it's easy to compute stuff with the sine wave, since the properties of sine waves are simple, such that at time 0 or at degree 0, the value of the voltage, the current, the power is 0. So this right here is very easy to remember. The sine looks like a mountain, where 0 is on the ground. Cosine is the opposite. 1 is the starting point, and then it looks like pretty much like a bowl, like a cup. So a sine alpha is the same thing as sine omega t. But remember, omega is 2 pi f. So this whole thing is expressed as a times sine times 2 pi f. So if the value in the vertical axis is current, then your amplitude will be the current value. If your value is voltage, the amplitude will be voltage. The frequency stays the same. If it's power, the amplitude will be power. So this is what determines what physical quantity is traveling with the wave. So, for example, sketch the energy wave that has 10 times sine of 314 t with the abscissa. So, t is going to be the variable in the x-axis. If you notice here, right here is t. 10 is going to be the amplitude. So this is going to go from 0 to 10. And 314 is 2 times pi times f. Okay? So 314 equals 2 times pi times f. The only thing that you don't know is f, the frequency. So you have 314 and you have 2 times pi. So 314 divided by 2 pi, or the other way around, 2 pi divided by 314, because we want to find, depending if you want to find the cycles or the frequency. So if you want to find the cycles or the period, is basically 2 pi divided by omega, and is 2 pi divided by omega, and omega is 314. So if you go back to the drawing board to make sure that we have this correct. So we're saying that omega equals 2 pi f. We know this number, of course. We know that this is a number, the calculator, or just type pi, your calculator will have pi. And we don't have f, but they're telling you that the general form of the wave is a times sine times 2 pi f t, or this could be 2 pi fx, depending on the argument, right? Depending on the y-axis, the x-axis. The general form is t plus a shift. Okay, so if I do that again, a times sine 2 pi f t plus a shift. So in this case, shift is 0. We don't have to worry about that. We don't know the frequency yet, but the t is just the value, the argument that you're going to be putting into the sine function. So when t equals 0, your function is going to be here. When t equals 45 degrees, it's going to be 1. When t equals 90, is 0. When t equals 270, is minus a. When t equals 360 degrees, is 0. So this is how you form your sine wave, right? Right now they're telling us that we have 314. Let me write down 314 equals 2 pi f. So 314 divided by 2 pi equals, so let's do, if we go back to our code right here, so t, let's say omega equals 314, and we know that, let's put a comment here, we know that omega equals 2 times pi times frequency. We want to find frequency, so let's call this W instead of omega. So we just have to divide by 2 pi. So frequency equals W divided by pi. But how do we call pi in Python? We just have to say, we kind of have to call the math library, which in Python is called numeric package. So can I move this up? Okay, yes, import numeric package from Python, and I'm gonna do an alias, and I'm gonna say as np. So just basically say call John, or sorry, call Jonathan, and which I call him John. So call John. Basically, this is the, don't let me confuse you here. This is, since remember, computers only know how to do summation and subtraction and multiplication and division. In order to do pi, which pi, I can type pi equals 3.1415, but I want to use the pi constant already saved in the programming language that has thousands of values stored up to the decimal point. So I'm going to call that value, which is in a library called numeric library from Python, numpy. And np is just an alias. So this is a rule of thumb. So you'll see why. So that when I say np, numpy, 2 times pi, np pi. Correct. Now I know. So this, let me show you something else why I'm doing this. Print np pi. Right? So I get a bunch of decimals for more accuracy. If I do numpy, it's the same thing. numpy.pi. Because now it doesn't, if I do this, correct? There you go. So now instead of numpy, I'm gonna say, hey, instead of, your name is Michael, but I call you Mike, so instead of Michael, I'm gonna say Mike. Instead of numpy, I'm gonna say np. So anytime I need to use numpy library, which will give me values of pi, values of Euler, any number, throughout the course you'll see how powerful this library will be. So numpy, it's going to be np pi. Okay, run it. Excellent. Alright, so we will do W omega divided by 2 pi, and we're going to do printf, which is frequency. 49.97 hertz. Let me see something here. And t equals 1 divided by frequency, and print t. I think I did this the wrong way. What are the units of 314? let me go back to the presentation. So we're saying that sketch 314 is omega, and omega has units of radians per second. Omega has units of radians per second, right? So 314 radians per second is giving me, oh, I see, I am doing omega equals 2 pi divided by the period. This is what I'm doing here. Okay, now I get it. Sorry, I got confused. So let's do this again. So we're gonna say find the alpha in degrees. Remember, what is alpha? Alpha is 2 pi f times the time times the t variable. So the period is 2 pi divided by omega, right? Period is 2 pi divided by omega. Omega is 314. So I'm doing the opposite. So I'm gonna do period equals 2 pi 2 pi divided by omega. And now print t. Let's print this one. Now we get it. So it's 0.2, which is the same thing we got here. Okay, so it's 0.02 or 20 milliseconds. Okay. 20 milliseconds. Now, if we want to find the frequency, the only thing we have to do is frequency is 1 over t and this is frequency. There you go. So yeah, we did it correctly. So just wanted to confirm this is 49.97 or 50, okay, hertz, 50 hertz. So they did not ask for this answer in hertz, but we know that 314 radians per second corresponds to 50 hertz, which is this type of voltage that they get in Europe. So going back to this, we can say that for those of you who want to learn Python, this would be a good way of doing this. The period is this, and the frequency is then the units are hertz. So quotation mark is for the comments when you print something. The period is, and the frequency is 50 hertz. Okay, that's good. Going back to the problem here. Okay, so find the angle in degrees. That's pretty simple. We know that sine starts from 0, then middle point is 180, and then the final point is 216. So this is very simple. Find the angle in radians. So that should be pretty simple as well. We just know that 180 is pi and 2 pi is 216, and we know that pi over 2 and 3 pi over 2 are the middle point. And the time in seconds, we also did that, which is 20 milliseconds. So one period takes 20 milliseconds. Okay, so very simple stuff. If they give you to recap. If they give you the, do this again. If they give you, say, say voltage equals a constant times sine of omega t, this t is the argument to the function. Okay, so this t is just going to be from 0 to, depending on the domain, if it's in seconds, if it's in radians, you transfer it to radians. If it's in degrees, you transfer it to degrees. So this is a chain of numbers, of an array of numbers that you're going to be inputting to your sine wave to be able to build your sine wave. But this omega part right here, this is 2 pi f. So since they told us that this is 314, we know that this 314 equals 2 pi f. Alright, and then in that case, since we want to know what's f, we just simply do 314 divided by 2 pi, and if we want to know the period, we just do 1 over f. Okay, so 314 divided by 2 pi, we did that before, that gives us 49.97 or 50 hertz. And 1 divided by 49.97, we did that, gives us 0.02, which is equal to 50 hertz. So this equals 50 hertz, and this is equal to 20 milliseconds. Okay, simple stuff. Now, the other thing that we need to characterize, we talked about frequency and period, we talked about amplitude, and the other thing we need to characterize is the phase. The phase is theta, and is pretty simple as well. So, when they show you 2 pi negative phase, or they show you a negative phase, there's a shift. There's a shift from the vertical axis. So this is the theta shift right here. Okay, so sorry, let me say that again. It's counterintuitive. When they give you plus, the shift is to the left, because this point now has shifted negative, or has shifted a value of theta. Okay, so when it's plus, the wave shifts to the left. Okay, when it's negative, the wave shifts to the right. And of course, since this wave is continuous, then what this one wasn't 0, now of course there's gonna be starting from a different point. Okay, so the initial point is negative a sine theta. Here the initial point is a sine theta. And I was telling you earlier that you can transfer a cosine wave to a sine wave when they're shifted by 90 degrees. So a sine wave is the same thing as a cosine wave that is shifted in 80 degrees. For example, sine of omega t, that's sine of 2 pi f times t, plus 90, or times pi over 2, this is in radians, this is in degrees. This is the same thing as cosine of 2 pi ft. Okay. Similarly, sine omega t is the same thing as cosine of the same angle, the same arguments, but negative 90 in degrees, or negative pi over 2 in radians. This is going to be very useful because remember that the derivative of 1 of sine is cosine, so you can get the derivative of sine in terms of sine with a shift, which is what we're going to start doing when we learn about circuits. Now, the things that we use for function generator and how to actually produce the waves with hardware are called function generators, and we'll see these when we go to the lab. And basically the way that they operate is that will give you a frequency range. So that's when you buy one, you basically talk to the manufacturer about your needs. So this one is a pretty small range, it's 0.5 to 4 megahertz. So this will give you, this particular one could give you like waves for people to be able to hear something. So small frequency. The waveforms give you, so they're gonna have sine, square, triangle. So the types of generally you use different types to characterize your circuit. You want to see how your circuit behaves given different types of waves, because of course we're talking about sine wave, right? So this is going to be sine. Cosine, we saw this the opposite. We have a triangular wave. Okay, we have, interestingly, we'll learn that you can get this by adding capacitors, resistors. So it's pretty cool how you generate these waves, because they're not magic, they're generated by the function generator. But how does the function generator work? We're gonna learn. If you open up a function generator by the end of this class, you should be able, by the end of this course, you should be able to see all the components and see, okay, this is how they do this part, this is how they do that, etc. Then you have another one, which is a square wave, which is very useful to PWM. PWM, pulse width modulation. And this is great because if you think of zeros and ones, this is a pretty good example how to operate with a digital controller, a digital system. And you have other waves, etc., or combinations of waves. Okay, you have sine that has different frequencies, and etc. You can have RAM, like pulse, etc. The amplitude is in terms of peak to peak. Okay. We have terms of dB, which we have impedance. We'll talk about impedance. Distortion, if you want to have a wave that is distorted to module or to characterize noise. We have rise and fall times. We'll talk about that. We have different waveforms. We saw that. We have impedances, input and output. So this is a function generator that you will use so that you don't have to plug in your circuit to the wall, which could be pretty dangerous. This has all the safety diodes and fuses that you don't break your circuit or you don't get hurt. So when you operate with AC circuits, you want to get a hand on a function generator. Another thing, so the function generator is to generate the inputs. To see the output or to study the circuit, you use oscilloscope, and the oscilloscope is pretty similar. You basically see the wave on the screen, and if you notice, this is the input wave, for example, because this could be the wave after your circuit, after going through a filter, a capacitors, etc. And the way you study the wave with or the output with an oscilloscope is depending on the sensitivities on the axis. So in this particular case, we're setting up with the menu. For instance, you go to the menu and say the vertical sensitivity is going to be 0.1 volt per division, and the horizontal sensitivity is going to be 50 microseconds per division. So micro is 10 to the negative 6. Okay, milli is 10 to the negative 3. So milli, this is micro, and this is little m, and this is mu. Pico is 10 to the negative 12. Nano is 10 to the negative 9. So this is microseconds, 10 to the negative 6 per division. So if a period is 4 divisions, then we're gonna have each division is 50 microseconds per division. 50 microseconds per division. So we're saying that the period is going to be from the initial point to the final point. So we have initial point, then we have 1 division, 2, 3, 4 divisions. So this is a whole cycle. Therefore, a whole cycle has 4 divisions, and each division is 50 microseconds. So division cancels with division, by 50 microseconds per division. and we have 4 divisions, so 40 divided by 50, sorry, 40 times 50 microseconds is 200 microseconds. So this period takes 200 microseconds. If you want to find the frequency, you simply do 1 divided 200 microseconds. Right, so that's what we did, and we have 5 kilohertz is the frequency. Now the amplitude is 2 divisions, is peak to peak, right? So we only take the positive part to get the peak to peak because it's symmetric. That's the nice thing about waves, they're symmetric. And we have 2 divisions. So it's 0.1 volt per division. So 0.1 volt per division times 2 divisions is 0.2 volts. So this wave is equal to peak to peak, or not necessarily peak to peak, just voltage, because V peak to peak is 4, right? V peak to peak is 4 because it's from -2 to 2. But the way to characterize this voltage wave in terms of time, as a function of time, is going to be 0. Oh, this is 0.4. My bad, it's 0.4. So even though here's 2 divisions, we have to do 2 divisions times 0.1 division per voltage per division. So it's voltage is 0.2 volts times, this is a cosine wave, cosine of 2 pi f, which is 5 kilohertz, no units, so we don't need the units, times t, 2 pi 5, so this is 10 pi, 10 pi t, and close parentheses. So let me write it again. V as a function of time, because we're gonna input seconds, and the units are seconds for the horizontal axis. We have V equals 0.2 times cosine of 10 pi t, and this is volts. This is units of volts. Now, since we want to say cosine in terms of sine, Vt equals 0.2 times sine of 10 pi t, and remember here we said that cosine is the same thing as sine plus 90 degrees. Okay, so plus, and when we go here we say 90 degrees.